For a topical guide to this subject, see Outline of Order Theory. Order theory is a branch of mathematics which investigates our intuitive notion of order using binary relations. It provides a formal framework for describing statements such as, "this is less than that," or "this precedes that." This article introduces the field and provides basic definitions. A list of order theoretic terms can be found in the Order Theory Glossary. Background and motivation. Orders are everywhere in mathematics and related fields like computer science. The first order often discussed in primary school is the standard order on the natural numbers, e.g., 2 is less than 3, 10 is greater than 5, or does Tom have fewer cookies than Sally? This intuitive concept can be extended to orders on other sets of numbers, such as the integers and the reals. The idea of being greater than or less than another number is one of the basic intuitions of number systems in general. Another familiar example of an ordering is the lexicographic order of words in a dictionary. The above types of orders have a special property. Each element can be compared to any other element, i.e., it is greater, smaller, or equal. However, this is not always a desired requirement. For example, consider the subset ordering of sets. If a set A contains all the elements of a set B, then B is said to be smaller than or equal to A. Yet there are some sets that cannot be related in this fashion. Whenever both contain some elements that are not in the other, the two sets are not related by subset inclusion. Hence, subset inclusion is only a partial order, as opposed to the total orders given before. Order theory captures the intuition of orders that arises from such examples in a general setting. This is achieved by specifying properties that a relation must have to be a mathematical order. This more abstract approach makes much sense, because one can derive numerous theorems in a general setting, without focusing on the details of any particular order. These insights can then be readily transferred to many less abstract applications. Driven by the wide practical usage of orders, numerous special kinds of ordered sets have been defined, some of which have grown into mathematical fields of their own. In addition, order theory does not restrict itself to the various classes of ordering relations, but also considers appropriate functions between them. A simple example of an order theoretic property for functions comes from analysis where monotone functions are frequently found. Basic definitions. This section introduces ordered sets by building upon the concepts of set theory, arithmetic, and binary relations. Partially ordered sets orders are special binary relations. Suppose that P is a set and that is a relation on P, then is a partial order if it is reflexive, antisymmetric, and transitive, i.e., for all A, B and C in P, we have that. Or if a B and B are then A equals B, if a B and B C then a C. A set with a partial order on it is called a partially ordered set, poset, or just an ordered set if the intended meaning is clear. By checking these properties, one immediately sees that the well-known orders on natural numbers, integers, rational numbers and reals are all orders in the above sense. However, they have the additional property of being total, i.e., for all A and B and P, we have that, a B or BA. These orders can also be called linear orders or chains. While many classical orders are linear, the subset order on sets provides an example where this is not the case. Another example is given by the divisibility relation. For two natural numbers n and m, we write n, m if n divides m without remainder. One easily sees that this yields a partial order. The identity relation equals on any set is also a partial order in which every two distinct elements are incomparable. It is also the only relation that is both a partial order and an equivalence relation. Many advanced properties of posets are interesting mainly for nonlinear orders. Visualizing a poset Hasse diagrams can visually represent the elements and relations of a partial ordering. These are graph drawings where the vertices are the elements of the poset and the ordering relation is indicated by both the edges and the relative positioning of the vertices. Orders are drawn bottom up. If an element x is smaller than y, then there exists a path from x to y that is directed upwards. It is often necessary for the edges connecting elements to cross each other, but elements must never be located within an edge. An instructive exercise is to draw the Hasse diagram for the set of natural numbers that is smaller than or equal to 13, ordered by. Even some infinite sets can be diagrammed by superimposing an ellipsis on a finite suborder. This works well for the natural numbers, but it fails for the reals, where there is no immediate successor above 0. However, quite often one can obtain an intuition related to diagrams of a similar kind. Special elements within an order. In a partially ordered set, there may be some elements that play a special role. The most basic example is given by the least element of opposite. For example, 1 is the least element of the positive integers and the empty set is the least set under the subset order. Formally, an element M is a least element if MA for all elements are of the order. The notation 0 is frequently found for the least element, even when no numbers are concerned. However, in orders on sets of numbers, this notation might be inappropriate or ambiguous, since the number 0 is not always least. An example is given by the above divisibility order, where 1 is the least element since it divides all other numbers. In contrast, 0 is the number that is divided by all other numbers. Hence it is the greatest element of the order. Other frequent terms for the least and greatest elements is bottom and top, or 0 and unit. Least and greatest elements may fail to exist, as the example of the real numbers shows. But if they exist, they are always unique. In contrast, consider the divisibility relation on the set 2, 3, 4, 5, 6. Although this set has neither top nor bottom, the elements 2, 3, and 5 have no elements below them, while 4, 5, and 6 have none above. Such elements are called minimal and maximal, respectively. Formally, an element M is minimal if M implies or equals M for all elements are of the order. Exchanging with yields the definition of maximality. As the example shows, there can be many maximal elements and some elements may be both maximal and minimal. However, if there is a least element, then it is the only minimal element of the order. Again, in infinite poses, maximal elements do not always exist. The set of all finite subsets of a given infinite set, ordered by subset inclusion, provides one of many counterexamples. An important tool to ensure the existence of maximal elements under certain conditions is Zorn's lemma. Subsets of partially ordered sets inherit the order. We already applied this by considering the subset 2, 3, 4, 5, 6 of the natural numbers with the induced divisibility ordering. Now there are also elements of opposite that are special with respect to some subset of the order. This leads to the definition of upper bounds. Given a subset S of some poset P, an upper bound of S is an element B of P that is above all elements of S. Formally, this means that SB, for all S in S. Lower bounds again are defined by inverting the order. For example, -5 is a lower bound of the natural numbers as a subset of the integers. Given a set of sets, an upper bound for these sets under the subset ordering is given by their union. In fact, this upper bound is quite special. It is the smallest set that contains all of the sets. Hence, we have found the least upper bound of a set of sets. This concept is also called supremum or join, and for a set S one writes sup or for its least upper bound. Conversely, the greatest lower bound is known as infimum or meton, denoted INF4. These concepts play an important role in many applications of order theory. For two elements x and y, one also writes and for sup and INF, respectively. For another example, consider again the relation on natural numbers. The least upper bound of two numbers is the smallest number that is divided by both of them, i.e., the least common multiple of the numbers. Greatest lower bounds in turn are given by the greatest common divisor. Duality. In the previous definitions, we often noted that a concept can be defined by just inverting the ordering in a former definition. This is the case for least and greatest, for minimal and maximal, for upper bound and lower bound, and so on. This is a general situation in order theory. A given order can be inverted by just exchanging its direction, pictorially flipping the Hasse diagram top down. This yields the so-called dual, inverse, or opposite order. Every order theoretic definition has its dual. It is the notion one obtains by applying the definition to the inverse order. Since all concepts are symmetric, this operation preserves the theorems of partial orders. For a given mathematical result, one can just invert the order and replace all definitions by their duals, and one obtains another valid theorem. This is important and useful, since one obtains two theorems for the price of one. Some more details and examples can be found in the article on duality in order theory. Constructing new orders. There are many ways to construct orders out of given orders. The dual order is one example. Another important construction is the Cartesian product of two partially ordered sets, taken together with the product order on pairs of elements. The ordering is defined by if of B and XY. The disjoint union of two poses is another typical example of order construction, where the order is just the union of the original orders. Every partial order gives rise to a so-called strict order less than, by defining a less than B if a B and not BA. This transformation can be inverted by setting a B if a less than B or A equals B. The two concepts are equivalent, although in some circumstances one can be more convenient to work with than the other. Functions between orders. It is reasonable to consider functions between partially ordered sets having certain additional properties that are related to the ordering relations of the two sets. The most fundamental condition that occurs in this context is monotonicity. A function f from a poset P to a poset Q is monotone, or order-preserving, if a B in P implies ff in Q. The converse of this implication leads to functions that are order-reflecting, i.e., functions f as above for which ff implies a B. On the other hand, a function may also be order-reversing or antitone, if a B implies ff. An order embedding is a function f between orders that is both order-preserving and order-reflecting. Examples for these definitions are found easily. For instance, the function that maps a natural number to its successor is clearly monotone with respect to the natural order. Any function from a discrete order, i.e., from a set ordered by the identity order, equals, is also monotone. Mapping each natural number to the corresponding real number gives an example for an order embedding. The set complement on a power set is an example of an antitone function. An important question is when two orders are essentially equal, i.e., when they are the same up to renaming of elements. Order isomorphisms are functions that define such a renaming. An order isomorphism is a monotone bijective function that has a monotone inverse. This is equivalent to being a surjective order embedding. Hence, the image f of an order embedding is always isomorphic to P, which justifies the term embedding. A more elaborate type of functions is given by so-called Galois connections. Monotone Galois connections can be viewed as a generalization of order isomorphisms, since they constitute of a pair of two functions in converse directions, which are not quite inverse to each other, but that still have close relationships. Another special type of self-maps on opposite are closure operators, which are not only monotonic, but also idempotent, i.e., f equals f, and extensive, i.e., xf. These have many applications in all kinds of closures that appear in mathematics, besides being compatible with the mere order relations. Functions between poses may also behave well with respect to special elements and constructions. For example, when talking about poses with least element, it may seem reasonable to consider only monotonic functions that preserve this element, i.e., which map least elements to least elements. If binary infima exist, then a reasonable property might be to require that f equals ff for all x and y. All of these properties, and indeed many more, may be compiled under the label of limit-preserving functions. Finally, one can invert the view, switching from functions of orders to orders of functions. Indeed, the functions between two poses p and q can be ordered via the pointwise order. For two functions f and g, we have fg if fg for all elements x of p. This occurs for example in domain theory, where function spaces play an important role. Special types of orders. Many of the structures that are studied in order theory employ order relations with further properties. In fact, even some relations that are not partial orders are of special interest. Mainly the concept of a preorder has to be mentioned. A preorder is a relation that is reflexive intransitive but not necessarily antisymmetric. Each preorder induces an equivalence relation between elements, where A is equivalent to B, if A B and B A. Preorders can be turned into orders by identifying all elements that are equivalent with respect to this relation. Several types of orders can be defined from numerical data on the items of the order. A total order results from attaching distinct real numbers to each item and using the numerical comparisons to order the items. Instead, if distinct items are allowed to have equal numerical scores, one obtains a strict weak ordering. Requiring two scores to be separated by a fixed threshold before they may be compared leads to the concept of a semi-order, while allowing the threshold to vary on a per-item basis produces an interval order. An additional simple but useful property leads to so-called well orders, for which all non-empty subsets have a minimal element. Generalizing well orders from linear to partial orders. A set is well partially ordered if all its non-empty subsets have a finite number of minimal elements. Many other types of orders arise when the existence of infima and suprema of certain sets is guaranteed. Focusing on this aspect, usually referred to as completeness of orders, one obtains bounded poses, i.e., poses with the least and greatest element. Lattices, in which every non-empty finite set has a supremum and infimum. Complete lattices, where every set has a supremum and infimum, and directed complete partial orders, that guarantee the existence of suprema of all directed subsets and that are studied in domain theory. However, one can go even further. If all finite non-empty infima exist, then can be viewed as a total binary operation in the sense of universal algebra. Hence, in a lattice, two operations are available, and one can define new properties by giving identities, such as x equals, for all x, y, and z. This condition is called distributivity and gives rise to distributive lattices. There are some other important distributivity laws which are discussed in the article on distributivity in order theory. Some additional order structures that are often specified via algebraic operations and defining identities are Hating algebras and Boolean algebras, which both introduce a new operation tilde called negation. Both structures play a role in mathematical logic, and especially Boolean algebras have major applications in computer science. Finally, various structures in mathematics combine orders with even more algebraic operations, as in the case of quantales, that allow for the definition of an addition operation. Many other important properties of poses exist. For example, a poset is locally finite if every closed interval a, b, in it is finite. Locally finite poses give rise to incidence algebras, which in turn can be used to define the Euler characteristic of finite bounded poses. Subsets of ordered sets. In an ordered set, one can define many types of special subsets based on the given order. A simple example are upper sets, i.e., sets that contain all elements that are above them in the order. Formally, the upper closure of a set S in a poset P is given by the set X in P. There is some Y in S with YX. A set that is equal to its upper closure is called an upper set. Lower sets are defined dually. More complicated lower subsets are ideals, which have the additional property that each two of their elements have an upper bound within the ideal. Their duals are given by filters. A related concept is that of a directed subset, which like an ideal contains upper bounds of finite subsets, but does not have to be a lower set. Furthermore, it is often generalized to preordered sets. A subset, which is, as a subposit, linearly ordered, is called the chain. The opposite notion, the anti-chain, is a subset that contains no two comparable elements, i.e., that is a discrete order.